Okay, another factor that affects the rate of an SN1 and SN2 reaction besides the structure of the substrate of the alkyl halide. Okay, so solvent also play roles in terms of facilitating or slow down the rate of this SN1 or SN2 reaction. All right. At the end, you should be able to pick an appropriate solvent for a reaction that you're doing, either an SN1 or SN2. Okay. Before that, let's take a look at the most solvent that you're gonna see. Okay, all these are polar solvent, of course, right? But they are slightly different. On the left side, we call polar protic solvent. Protic means proton, so it's got proton on oxygen, on nitrogen. Okay, and this type, these four solvents can form hydrogen bonding between itself, like in solution of water, in solution made by methanol, in solution of ethanol, in solution of acetic acid. They can form hydrogen bonding. All right, just review real quick. So if you want to form hydrogen bond, you need an OH and an oxygen, an NH and another nitrogen, and FH and another fluorine. All right, but you're not going to see a solvent that have fluorine on it. So just these two right here. All right, so they can form hydrogen bonds. All right, so we call polar protic solvent. On the right side, we call polar aprotic solvent because it doesn't have proton on it, right? And so the interaction that they can form just a dipole. Of course, acetone can form hydrogen bond as a hydrogen bond acceptor when you mix acetone with water, acetone with methanol, ethanol, or acetic acid. But by itself, it cannot form a hydrogen bond. That's my point. All right, it can if you mix with the hydrogen bond donor, but they can be only an acceptor. All right, all this, the main interaction of all this solvent is just dipole, so we call polar aprotic solvent. All right, so polar aprotic solvent facilitate SN1 and SN2 differently. You have to be able to pick which one go with SN1, which one go with SN2, and why. That's the most important thing. Don't just memorize it. All right? You need to be able to explain why we use polar protic solvent for this reaction, why we use polar aprotic solvent for this reaction, and why not the other. Okay. All right, let's take a look at the first one. Let's say if you want to do an SN1 reaction, all right? Think about an SN1 reaction. What controls the rate of an SN1 reaction? Well, the rate determining step is a carbocation formation. If carbocation is stabilized, the reaction goes quick, right? If you use polar protic solvent with an SN1 reaction, right? Polar protic solvent can form hydrogen bond, stabilize the whole intermediate, right? Here, this is the transition state. Bond is about to break, right? So we can use the oxygen to form hydrogen bond with, from interaction, stabilize the carbocation. They can use the proton, which is partially positive, stabilize the bromide ion, right? So the whole transition state is more stable compared to without a solvent. All right. So with this stabilization, the activation energy of the transition state is lower. The reaction goes faster. Okay. So polar protic solvent, SN1, go together because the carbocation is stabilized. All right. Now, what if we use aprotic solvent? Why not aprotic solvent? Well, a polar aprotic solvent can stabilize only the cation, which is right here. So bromine leaves, you about to get carbocation right here. They can use oxygen to stabilize this semi-carbocation, but they cannot stabilize bromide. All right. Some of you may ask, hey, hold on, this acetone also got partially positive carbon, right? Should be able to stabilize bromide. Yes, but it cannot because steric hindrance of the two methyl group right here. Yeah? It cannot stabilize bromide effectively. So we just say it doesn't stabilize the anion, right? So this compared to when they were in a protic solvent is relatively unstable. It's stable, right? But it's relatively unstable compared to when you use protic solvent, right? All is the same thing. So sulfur positive, of course, but it got sterically hindered to methyl group around it. It's really difficult to stabilize the negative charge, right? But oxygen is wide open, can stabilize the positive charge there. Okay. So polar protic solvent can stabilize only the cation, leave the carbocation still high in energy. and the reaction is relatively slower compared to a product solvent. Let's take a look right here. So let's say if you do the same reaction, but one reaction you use polar product solvent, and the other one you use polar product solvent, right? Use polar product solvent. Product solvent can stabilize both cation and anion. So the level of transition state is lower activation energy, so it goes faster. Okay. Yeah, a product solvent can stabilize only the carbocation, leave bromide still unstabilized, so the activation energy is higher and reaction goes slower. Okay. All right. Now, an SN2. Let's say you want to do an SN2 reaction, use a product solvent, and here's the reason why. Right? For a product solvent, if you still remember in SN2. The reaction mechanism happened in one step, right? Just one step reaction, nucleophilic attack, bromine leaves, leaving group leave, and you get the product right there. Since a product solvent can stabilize only cation, it will leave the nucleophile or anion alone, which is the best thing that you can do. Keep the nucleophile reactive because the reaction will go fast if the nucleophile is reactive, right? And a product solvent do just like that, stabilize only the only the cation, leave an ion reactive. So hydroxide still stay reactive, attack the alkyl halides. So we call naked nucleophile. So nothing around it. This solvent leave nucleophile alone. It will retain nucleophilicity. Okay, and it's high nucleophilicity. High nucleophilicity nucleophile will facilitate an SN2 reaction. All right. Compared to a product solvent, which is a better solvent in terms of stabilize any compound, any positive charge, any negative charge in the solution. Well, this is what we don't want to happen. Can stabilize both cation and anion. And when you stabilize an anion, well, the nucleophilicity of this hydroxide will be lower, right? Will be lower. So this is from the textbook. The solvent can form cluster or solvent cage, whatever you want to call it. So basically, it's reduce the nucleophilicity of the nucleophile. So the nucleophile is not as reactive, and the reaction goes more slowly, basically. All right. So decrease the nucleophilicity of the hydroxide. All right. Let's say if you do exactly the same SN2 reaction, but use different solvent, all right? Go back here. Okay. If you use a polar product solvent who can form a hydrogen bond, right? Let's say water. Water can stabilize hydroxide. What happened? Well, it's more stable. When it's more stable, come down here, the energy level is lower, higher activation energy to overcome. See that? Compared to a polar product solvent that leave nucleophile alone. So the nucleophile stay reactive and the activation energy is small. So the SN2 reaction goes more quickly. Okay? So my point is, for an SN1 reaction, you want to stabilize the whole thing. Product solvent, the best one to go, can stabilize cation and anion. But if you want to do SN2 reaction, which the rate depends on, whose rate depends on the nucleophilicity, you want to leave the nucleophile alone. What's the best option? A product solvent, it leaves nucleophile alone. All right. All right, so let's take a look at some numbers so you get more clear right here. This is a real experiment, right? So the nucleophile on A side look like that. So there's one of nitrogen will attack that carbon of bromine, okay? And this is an SN2 reaction. And let's take a look at the rate in this solvent, all right? The first two are polar product solvent, right? Can form hydrogen bond with the nucleophile. Basically reduce the nucleophilicity of A side. All right. Polar A product solvent leave A side alone, stay reactive. Okay. Look at the relative rate. All right. The slow rate for polar product solvent reduce the nucleophilicity of the nucleophile. Polar product solvent leave nucleophile alone. The rate is much faster. Okay. The difference between polar A product solvent, the difference of the rate between polar A product solvent depends on which one stabilize the nucleophile less. basically, right? Cyanide does not really stabilize SI. SI really free high nucleophilicity. The reaction rate goes much more quickly, all right? Okay, so for SN2, go polar aprotic solvent. Okay. All right, so if you can differentiate which one's a polar aprotic, which one polar protic, you know which one go SN2, which one go appropriate for SN1 or appropriate for SN2. And OH, the first one, ethanol. Good solvent is a polar protic solvent that can form hydrogen bond. This one good for stabilized cation and anion. This is for SN1 reaction. This one, dimethyl sulfoxide or DMSO, doesn't have an OH. This is polar aprotic solvent, cannot form hydrogen bond, no hydrogen, so aprotic. Will leave nucleophile alone. This one go SN2. OH, right there, you see can form hydrogen bond. This is polar protic solvent, love to stabilize a carbocation, right, and anion. So good for SN1. This guy got hydrogen right here, but it's not connected to oxygen or nitrogen. Cannot form hydrogen bond. Okay, so this is a polar aprotic solvent. It will leave nucleophile reactive. Right, so SN2. Methanol, just like ethanol, same thing. This is a polar protic solvent, SN1. Right. We have acetonitrile, so a CH3CN. No hydrogen or nitrogen. So this guy is a polar aprotic solvent, good for SN2. Lastly, nitrogen connect to hydrogen for sure. This is a polar protic solvent, SN1 for sure. That's how we think about things. All right. So if you can differentiate polar protic, polar aprotic, you should be able to tell which one go SN1, which one good for SN2. All right. Okay. Let's go to the next video.